Okay, next, the EA here is the product, or when we turn the shaft, connect to the external rotating mechanism, we produce EA. But the internal generated EA is not the voltage that appears on the terminals of VT. So this should be well known, because EA here will drop by the way it goes to the VT. So this is our V terminal, or V connected to the load. So this is our VT. So generated here, it drops around R armature X1, XS here, due to the armature reaction of XA. So we have here XA, or sometimes you write as X. So the distortion of the air gap magnetic field by the flowing of the that flows in the stator. So this is our stator. So this is our stator. This is rotating rotor. So XA is the armature reaction. XA here, armature reaction. And we have here self inductance of the armature coils, X1 or XA. X1 or XA, the big A. So that is a self inductance. And we have here the stator resistance of the armature, RA or RA big C, big RA or RA small. So RA, XA, XA here, self inductance, stator resistance, armature reaction. And also the effect of the sailing pole, rotor shape. So if we have here the rotating shape, maybe we have a sailing pole, and the pole is rotated outside, so we have some effect out of that. But due to minor or error compared to the non-sailing pole, it's ignored. Effect is ignored. So the main parts that remains to be considered is the RA, XA here, and XA on the armature side. Okay, if we take only the armature reaction factor, so the EA produced will drop throughout JX X here, plus how much it drop through or at the V phase or V terminal. So we can write EA is equal to IA times JX plus V phase or VT. So if we rearrange V phase over here, so V phase is equal to EA minus JX IA. This is our IA. So it will become the same equation as I mentioned. Okay, V phase equal to EA minus JX IA. So this is where we, when we consider the armature reaction of the output voltage. Then if we consider the factor number 2 of the self-inductance and also due to the stator resistance on the output voltage on the phase, the V phase is not going to be due to JXA, JXYA drop here only, not only due to this factor, but it will include also the other factor and the other 2 factor. So this is our self-inductance. This is the self-inductance element, whereby this is our stator resistance component. Stator resistance. So this is our self-inductance and stator resistance, as what we just discussed throughout this circuit just now. Stator resistance and self-inductance. So we combine the armature reaction effect and the self-inductance of the machine. Armature reaction effect, yeah, and self-inductance of the machine. So we will call as a synchronous reactance of XS. So XS here is equal to X plus XA, X armature plus X. So the overall equation become EA minus JXS minus RA IA. So XS is our synchronous reactant. Synchronous reactant. So XS is our synchronous reactant here. Okay, on the next slide, equivalent circuit. So if we have three-phase generator, so here are our field source to energize the field current and to create what so-called our flux. So this is our north and south. So the field will produce by the field source to produce the flux across our magnetic fields here. Okay, then we have three source of 3 point, what so called phase 1, phase 2 and phase 3. 3 point of source that deliver to the load, output to the load. So this is our 3 armature here, 1 field, 3 armature source. So V phase 1, phase 2 and phase 3. So we have EA1, EA2 and EA3. So all the EA here, the EA differ from V phase. So the EA produced at the terminal here is much bigger, for sure will be much bigger compared to the what produced at our terminal to the load. So here are the load connection. So it was differ from the due to the XS and also due to the impedance. Z is our impedance, XS is our synchronous reactance. So this is our XS here. So synchronous reactance. Total sum to be, when we add up with the SEF, this is our RA. RA just now is our stator resistance. This is our stator resistance. This is our impedance, synchronous reactance. Total are our impedance. So V terminal, when we reshuffle again the equation, equal to the generated voltage, internal voltage minus synchronous reactance minus the resistance here, armature resistance, stator armature resistance. Okay, per phase, that one is for the total 3 phase. For per phase equivalent circuit, we have here V phase equal to EA minus JXS minus RAIA. Meanwhile, our phase source is equal to JXF here times the IF times the JXF. Here the JXS and RA. Here only the JXF. Means that the higher the frequency, the lower the resistance. Later we should take a look details in our examples calculation. Okay, now we shall discuss the theory in terms of the trend and response. First, the machine, if we connected in Y, so Y connection, Y, another one is delta. So the voltage across the AC line, V line to line of the terminal equal to multiply of third 3 of the voltage. So V terminal cross here is equal to cert3 of V phase. So V phase is per phase. So this is one phase. So V phase is here. So V phase 1, phase 2 and phase 3. But the voltage across the overall terminal from line to line. So it combines of these two phases. Let's say this is phase 1, 2, 3. Combination of phase 2 and phase 3 to become V terminal. So V terminal is equal to cert3 of V phase. And you can see if you draw visually, you can see that the V phase each mass should be much lower compared to V terminal itself. So V terminal is at higher values or range compared to V phase. In terms of line current, I load are equal to the I phase. I that comes into the, if we're talking the generator, I that goes out from the phase is equal to I that go to the terminal. So I phase is equal to I line. So the same current flows out to the terminal. So I phase is equal to I line. So if you draw, you can see or you can appreciate much easier. If you connect in terms of delta connection, just not in Y, you can see that the V phase and V terminal are at par. So this is V phase, meanwhile this is V terminal. So they are both having the same range or same value. But in terms of current, you can see that the current that goes out from here, it will divide or it will mix between phase 1 and phase 2. Same goes to here. So means that V are the same, but in terms of current, I load are cert3 of I phase. I load here, I load are the amount of combination between I phase A and I phase B. So it's much bigger, should be much bigger. So the amount is cert3 of I phase. So the line current equal to multiply of cert3 of I phase current. Okay, in terms of phasor diagram, the voltage synchronous generator are usually expressed as phasors. Both phasors should be expressed in magnitude and angle. How much the degrees, how much the magnitude. So in 2D plot. So we shall draw, this is 0 angle, so this is the another angle. So usually we set 0 reference as a voltage as our reference. The incoming current and whatsoever will be the reference to the voltage. Okay, voltage in a phase, current in a phasor. This is phasor. In phasor. So how much the voltage? So V now we are referring to V phase or V out, and the current that goes or delivered to the load. Okay, then we go to the power factor consideration of our system, and we have learned about P equal to Q plus S, is it? So the P here, we have here real power, apparent power and reactive power. So this is P, this is Q, this is our S. So actually not P, Q. This is S equal to P plus Q. Okay, square. So actually we have the real power, we have reactive power, and the sum is our VA, or the total power that absorb or deliver to the load. So if you measure in terms of